Hello there. In this video, we're going to talk about some special properties of moment-generating functions, and we're also going to introduce a counterpart to the moment-generating function known as a characteristic function. So let us start off with some basic properties of the moment-generating function, and then we'll introduce our new friend. So the moment-generating function, recall, is defined to be equal to the expectation of the random variable e to the tx. So we used this relationship to prove the identity that the nth moment of the random variable x is precisely equal to the nth derivative of the moment-generating function of x evaluated at 0. So let's introduce another important property that is extremely useful. So this property says this. So if the moment-generating function of x of t is equal to the moment-generating function of y of t, where x and y are some random variables, and let's assume this is true for all values t in the set of real numbers, then what do we have? So if that is true, then the expectation of e to the tx must be equal to the expectation of e to the ty. So we can look at the Taylor's expansions of these things. So that's going to be equal to the expectation of 1 plus tx over 1 factorial plus t squared x squared over 2 factorial plus and so on must be equal to the expectation of 1 plus ty over 1 factorial plus t squared y squared over 2 factorial plus and so on. So we can distribute the expectation over, or we can subtract both sides by the expectations. So we can rewrite this as the expectation of 1 plus tx over 1 factorial plus t squared x squared over 2 factorial plus and so on, minus the expectation of 1 plus ty over 1 factorial plus t squared y squared over 2 factorial plus and so on. And this must be equal to 0. So by properties of expectations, this is like a random variable a and this is like a random variable b. So we know that the expectation of a plus or minus b is precisely equal to the expectation of a plus or minus the expectation of b for any random variables ab. So we can rewrite this expression as the expectation of 1 plus tx over 1 factorial plus t squared x squared over 2 factorial plus and so on minus 1 plus ty over 1 factorial plus t squared y squared over 2 factorial plus and so on. This must be equal to 0. So the expectation of something is equal to 0. This implies, so if the expectation of some variable z is equal to 0, that means that z must be equivalently equal to 0. This is very easy to verify. So if that is true, then that means this expression minus that expression must be equal to 0, which means those expressions must be equal. So that means 1 plus tx over 1 factorial plus t squared x squared over 2 factorial plus and so on must be equal to 1 plus ty over 1 factorial plus t squared y squared over 2 factorial plus and so on. So it's very easy to see that these 1's will cancel on both sides, and from here we can equate like powers of t. So I can look at the power of t to the first. So since this is the only linear term on both of these sides, then the coefficients must be equal. So from that we can see that x is equal to y. If we look at these terms, the like coefficients of t squared over 2 factorial is just going to be x squared and y squared. But you can verify that from the green expression that this is going to be equal to that. But in general we know that x to the n is going to be equal to y to the n from that original expression. So we have this theorem that if m of x of t and my of t are equal, then this is going to be true if and only if the variables x and y are precisely equal, which means these discrete random variables, and also continuous, are uniquely determined by their moment generating functions. So, important note about the moment generating function. So the moment generating function of x of t for some random variable x, which is equal to the expectation of e to the tx. Remember, if I choose some variables of x and for some constant t, that it's possible that this is going to be an infinite quantity, which could pose some problems. It could be possible for some random variable x, maybe not all, but it's possible that it is. So since we have this slight annoyance, this is what motivates us to introduce what we call the characteristic function. So the characteristic function is going to be another type of function for a random variable, and we're going to define it to be equal to phi of x of t to be equal to the expectation of the random variable e to the itx. Here, x is a random variable, t is a real number, and I is equal to the square root of -1. So xi is a complex number, and this, if you're familiar with Fourier series, is somewhat related to that. Alright, so what is so special about this, and does it have the same properties as the moment generating function? Well, it's very easy to prove that if phi of x of t equals phi y of t, then this is true if and only if x is equal to y. So it has that same property as moment generating functions, which is great. So another property of the characteristic function that the moment generating function does not have is the following. So the absolute value of phi x of t is going to be equal to the absolute value of its definition, which is the expectation of e to the I tx. So remember the triangle inequality. Remember that the absolute value of a plus b is always less than or equal to the absolute value of a plus the absolute value of b. So this is what we call the triangle inequality. And this is true for all complex numbers ab. So remember that expectation is actually just a sum. So this is the absolute value of sum. So by the triangle inequality, this must be less than or equal to the sum of the absolute values. Alright, so what does that mean? So also, how do we deal with this exponential? So remember that e to the I theta is equal to cosine of theta plus I sine of theta. This is what we usually refer to as Euler's identity. And this is very easy to prove from the Taylor series of cosine, sine, and the exponential. So if that is true, then that means this expression is precisely equal to the expectation of the absolute value of sine of tx plus I sine of tx. So what is the absolute value of that expression? So remember that sine and should be cosine in that first term. Let's rewrite that. So cosine of tx. There we go. Alright, so what does that exactly mean? So remember, in terms of the unit circle, cosine of x plus I sine of x is going to be a point that is located on the unit circle of radius 1. And remember that the absolute value tells us the distance from the origin of some complex number. And remember, this is going to be true for all values theta, and that's true for all values tx as well. So that means this absolute value is precisely equal to its distance from the origin, which is 1, and the absolute value of 1 is just 1, and the expectation of 1 is just 1 as well. So what we have here is that phi x of t, its absolute value, is always less than or equal to 1. So phi x of t is always less than or equal to 1. That means phi x is always bounded for any random variable x. And this is what makes characteristic functions a little bit unique from moment-generating functions. Now, there are two other properties that is true for both characteristic functions and moment-generating functions, and they are the following. So the first property is the characteristic function of the random variable cx of t. So let's just prove this out directly. So by definition, this is going to be equal to the expectation of the random variable e to the I t c x. So what I'm going to do, I'm going to let u be equal to tx. So that variable there. So this is going to be equal to the expectation of e to the I u. Where's my tx? It should be tc. So tc. So I'm going to define tc to be my constant. So that is going to give me iu of x, which by definition of the characteristic function is just the characteristic function of x in the variable u. But we already defined u to be equal to tc, so that means phi of cx of t is precisely equal to phi of x of ct. So if you have a constant multiplied by a random variable, you can just insert that to the parameter of the characteristic function. And one can also verify that the moment-generating function of cx of t is also equal to the moment-generating function of x of ct. So that's also an easily provable identity. 2. Let us assume that x and y are independent. So if x and y are independent, recall that the expectation of x times y is equal to the expectation of x times the expectation of y. If x and y are independent, you do not have this identity. So the question now becomes, what is the characteristic function of x plus y of t? So we can use our definition. That's just going to be the expectation of e to the I t x plus y. And we can distribute it across that sum. So we have that's just equal to the expectation of e to the itx times e to the ity. Since these are exponentials, we can just add those exponents together and decompose it there. So this is a random variable a, this is a random variable b. So if x and y are independent, a and b are also going to be independent as well, since they only vary by some exponential term, which is a constant. So that means this is going to be equal to the expectation of e to the itx times the expectation of e to the ity. So by the definition of the characteristic function, we have that phi of x plus y of t is precisely equal to phi of x of t multiplied by phi of y of t. So if you have the characteristic function of a sum of two variables, you can just multiply the individual characteristic functions of those random variables. And similarly, you can prove, in a very similar proof, that the moment generating function of x plus y can be also found to be equal to the product of the moment generating functions of the random variables x and y. And that's just some basic properties associated to both moment and characteristic functions for random variables, with the addition that the characteristic function is always bounded by 1 for any random variable x, which makes characteristic functions a tad bit more advantageous over moment generating functions. And we'll investigate how we can use characteristic functions to prove other important properties about random variables at a later time.